I'm Tilman Hinnerichs. I am a PhD student with Neil, but also with Sebastian Demancic, and I'm working on neurosymbolic program synthesis. I'm going to talk a little bit more about what that actually means. So I originally wanted to give like a little bit of a survey of neural program synthesis. So basically how to program with neural networks, basically. I voluntarily decided against it because I'm currently working on a project that I really like. And basically I'm going to present that project instead. So I'm going to try to connect it a little bit more to the actual seminar itself. So first off, a familiar situation. We are, well, almost all of us are computer scientists, and all of us have used an LLM or are using or have used LLMs somewhere in the process of developing some sort of software. And how you would usually use that is, well, if you try to ask for some code, give me a program written in Julia, in Python, or whatever, that translates a format A to format B, passes a bunch of tests, fixes an existing program, or I don't know, runs a useless command here. So we call this to formalize this a little bit, we are given a target language and we are given a specification where the Julia and Python is the target language and the other thing is a definition of what we want it to do. So why LLMs do work? Well, LLMs are just trained on tons and tons of data. So some would call them knowledgeable, some wouldn't. This is not up for discussion for now. They are also fast with a small asterisk over there. So basically they merge all these tons of data into a single model, and then just querying this model is a single or multiple queries to this one neural network. And they often work quite well. So they are actually exceptional at producing plausible solutions, which are mostly working. Why LLMs do not work? Well, mostly they produce syntactic errors. So they basically have no underlying knowledge about what the grammar of the actual programming language is. So if I just give it my favorite programming language of Orc or, I don't know, Fortran 95 or whatever, there might be a substantial chance that it just actually is not able to follow the proper syntactic structure of such programs. Second off, it has assumed semantics. So basically, just because a function is named print, it doesn't actually have to print stuff. It basically has no knowledge about what the function actually does. And if I, for example, in Python, redefine true to false, well, then it actually has no knowledge about what the actual thing is supposed to mean. And eventually, it cannot execute a program. Right? So for example, well, I can try to circumvent this a bit, but if I have a proposal program, it can't actually run the damn program, right? And figure out what actually went wrong. So all this is formalized in program synthesis. This is one of the oldest subfields of AI, if you want to say. It exists since the 60s, and it takes the exact same ingredients that we defined early on. So it basically takes a specification. You probably have seen this before. This is taken from Excel, from Microsoft Excel, where you literally have a bunch of mail addresses on the left-hand side, and you want to extract the first and the last name from it. And then you have this funny little dot at the bottom right, and you can drag it down. This is one of the most prominent applications of program synthesis that exist, but I mean, more prominent other ones exist. And then as a second ingredient, we take a target language. Well, this is just formalized by a grammar. So here, neatly hidden with the black bar. So literally, it's a context-free grammar. I think if you've studied computer science, you might have seen this before. So we have a symbol on the left-hand side, and then basically how to derive new structure from the symbol. So we can substitute an S with a concatenation of two different strings, and then we can recursively substitute the symbols again and again until we reach a program. Yeah, until we reach a program. This can look like this. So it's a concatenation of something of the first argument and so on. And as you may can see, this is a partial program. So here we just have a type in there, and this is to be substituted by something else. What I mean with a partial program, well, it's a program that is not finished yet. We still have to add a little bit of semantics over there to actually run the entire program. So how we find solutions in program synthesis? Well, in the worst case, we just enumerate all possible solutions from the grammar until we find a solution to our original program. As you can see, this grammar is, well, this well, is first off, produces infinitely many programs, and also second off, this is growing exponentially. So we, in the worst case, have to try a lot of programs. So what can we do about this? I'm first off going to introduce a few more applications here. So this is not just about programs. I usually talking to a lot more theoretical people. So they are usually not that interested in the applications themselves. I don't know, these are taken from some paper. I don't know. You can basically, I always used to say that basically everything is a program. Everything can be seen as an executable action of some sort. So for example, we have things from the planning domain where we can basically learn to write a program that stacks and unstacks towers or reorganizes them. It also has applications in symbolic regression, which is closely related, basically, where we try to find an approximation of an existing function with a symbolic definition, but there's also various applications in bioinformatics and whatnot. So why program synthesis and dissimilar? So far, we've talked a lot about programs and so on, and this is all very interesting. What does it have to do with this? Well, every program has an AST representation. So literally just these recursive substitutions that I just mentioned are literally just defining a tree. So basically, if we take the program that I've just defined, this is internally represented as an AST. And if I want to execute the program, then I usually do this bottom up. So basically, I take my first argument and I look at the certain index and so on. Okay. Now we want to make the bridge. So we have something like, for example, a neural network, and we want to use it for program synthesis. However, we cannot just use the LLM to just give us the programs, the solution program. So for example, here we have a parser program, and how we would go about this in the program synthesis case is we have this parser program. What is the next rule that I should use at this specific spot? You can think of this in a kind of reinforcement learning sense. I don't know, given this context, what is my next action and so on. But there's these ones in which this has similarities to many different other fields. So TLDR, we cannot just prompt the LLM for add every single choice because this is going to take very long. As I mentioned earlier on, there was a fast with a small asterisk over there. This is fast for most applications. This is not fast enough for program synthesis. Where one of the main strengths of program synthesis is testing a lot of programs, basically brute forcing the problem and then actually learning from those. And we want to keep that possibility. So if we at every single decision ask the LLM for all the possible choices and give us the best one, this is not going to end within our 10 hours of Delft time. So we have LLMs on the one side, which possibly give us wrong solutions, but plausible solutions, which is a little bit too expensive for our program synthesis domain. And on the other side, we have program synthesis in our wonderful library called HerbGL, which concretely follows specific grammars, which is very fast at enumeration, has some constraints, which I'm also going to introduce later on, but is by definition uninformed. It basically does not have a knowledge of what is useful to search for. It just knows it's going to be somewhere in this program space, but we don't know where. And now, ideally, we want to combine the two. We have the usefulness, what a plausible solution looks like from the LLM side, and we have all the theoretical background from the program synthesis side. Now we want to combine them. So TLDR, keep the guidance from LLMs and keep the discipline of synthesis. As a problem statement, we take an LLM, we take a target language, and we take a specification, and we want to find something that seems plausible with respect to the LLM, follows the grammar, and satisfies our specification. Now coming back to, well, how would we learn this? If we want to ignore the LLM, how do we want to learn this? Well, we are just literally just giving a bunch of data, we're giving a bunch of inputs, outputs, and satisfying programs. And then we want to learn a heuristic based on this. So given a specification, a bunch of grammar, and a program so far, this is a slide that I made when I wanted to still talk about the survey, actually. Which grammar rules are we supposed to pick? And this is going to look like this. I don't know, this is our program so far. And these are all the possible grammar rules that we can take. And then we get a prior over all of these. And then we're going to sample from this prior and so on. And well, and so on. What we are what I've found out after the first 1.5 years of my PhD is that this doesn't work too well, because programs themselves and the semantics of programs are difficult to predict in itself. So by itself, you need to know, eventually you need to train a network or a smaller network for a very small domain to learn about the semantics of a concrete program. And if you give, for example, an if then else or a while loop a slightly different semantics, well, it's going to change the entire behavior of the entire program, and the network has to figure this out. Well, we can cheat a bit. We can just use the LLM instead. Well, the LLM is already pre-trained on a lot of data, so we don't have to do it ourselves. So now we're skipping this entire part of learning the network and the priors ourselves, but we're literally just asking the LLM. So given an LLM, how can we get our proposals out such that we can use them for the program synthesis? And how this is usually done is literally just one of the most common ways is literally just encoding this into a PCFG. What PCFG means is it's a context-free grammar. So the grammar that I showed earlier on, well, somewhere here, is literally is context-free. So we have symbols on the left-hand side with no context attached to it. And we recursively substitute symbols here. And what a PCFG literally means, we just associate probability with these. So literally what we did here, these are probabilities associated to grammar rules. We literally do this for the entire grammar. And how this is commonly done is we just count occurrences of specific rules. We ask our LLM, what is the solution given this grammar and the specification? We get a bunch of proposals out, and we define our PCFG. As you can see, well, in its interpretation, likely programs are going to be explored earlier on, unlikely rules are going to be explored later on. Well, by definition, this doesn't have any knowledge about context. So literally what I said earlier on about the grammar, about the program so far, we don't take this into account. So what we are doing right now is we literally just take the program into account. So as said, what gets lost is the structural context and the use for subprograms and so on. And the intuition here is that LLMs are insanely good at what they're doing because they have a knowledge of what they did so far. They don't ignore the program so far, but they literally use the context so far as a prior to their next prediction. Good. So this is my current project that I'm currently working on, which is still work in progress. So the goal of this is to inject structural bias into the LLM guidance while keeping the correctness of the synthesizer. So instead of just counting the rules and the number of occurrences of specific rules, we take structural biases into account by, for example, counting the prefix alignment and reusing subprograms. And eventually, we want to use this as a prior towards our synthesis eventually. How this plays out is we get a score of a specific rule given the context, and this is a sum of three subscores, and then we basically sample programs according to its prior. We use 3 signals for this, which is, well, prefix alignment. The intuition is if similar programs used a specific rule after the same prefix pi, well, we just want to use R again. So for example, we have 8 proposals containing the prefix pi, and in 6 of them, the previous rules were, well, this specific rule over there. Then we want to use it again with a probability of 0.75. Well, then the second one is we want to reuse subprograms. So as I said earlier on, LLMs are quite neat at proposing useful substructures and so on. So the intuition here is if a fragment appears across multiple proposals, we want to use these rules jointly again. So what we are doing is if the fragment x+1 appears somewhere or in many proposals at the same time, then we're going to add this to our grammar or give the entire structure a joint score. And then the third signal, which is just, I think, the most important of the 3, is we want to emphasize exploration. So even though the first 2 are very nice and neat, we don't want to trust our LLM too much. Like we want given our proposals, we want to get quite close to those proposals, but we don't want to get stuck in the local minima. So the LLM's proposal might be faulty. Thus, we want to give a chance to less used terms at the same time. As an example, if a specific rule was overly used so far, we also want to give other rules a chance. As an intuition, for example, at the root, we have a little bit more support for the first signal, that is the prefix. So, for example, we have a strong contextual guidance near the root, and deeper down, we want to reuse the subprograms a little bit more. Current state of this. What do we gain from this? We get a cheap and context-aware guidance for a reliable program synthesis, and initial results that I cannot really show because I didn't prepare the plots yet. Is we do figure out that for some text-based, quite a few text-based domains, we get promising results of fewer candidates tested. Like we actually get a major improvement over naive LLM-based guidance, and even with pretty shitty LLMs like naive DeepSeek, for example, we get quite a bit of improvement, and we get a much faster discovery of satisfying programs. This is still ongoing work, so we have to formalize this. I put this small lambdas in this weighted sum over there. So we have to formalize this dependency a little bit more. We have to do a little bit more study on the proposal quality of the LLMs, and we have to do a little bit more evaluation eventually. Soon to be submitted to some workshop. Let's see. Good. Half a minute on the other stuff that I wanted to talk about. So this was neural program synthesis. Now I'm going to talk a little bit more about symbolic program synthesis to put it eventually together to neurosymbolic program synthesis. Well, grammars themselves are dumb, and the context-free grammar that I showed earlier on contains many, many programs that we just don't want to explore at all. So to put it briefly, grammars admit many syntactically correct but undesirable programs. I think in Neil's talk earlier on, it was called a cut. So literally just programs that we just don't want to explore, that are probably useless. So for example, programs that don't encode the input symbol, for example. If something is not dependent on the input, it's probably not useful. And then there's also many redundant programs. So for example, 1 times x, 1 times x plus 1. So basically anything with, including neutral elements. And for this, we can encode constraints or cuts, as I think many different fields have many different names for this. So we define a wonderful language of constraints with higher order constraints. It's a paper that we're currently writing, and it's currently above 50 pages already, because we're adding proofs and everything. It's going to get very neat soon, more on that later on, where you can, for example, encode constraints like these. So for example, we want to forbid any program structure that multiplies anything by int, or contains, or it must contain the input symbol x, or it must forbid anything, any addition plus 0, and we provide a constraint solver that actually enforces these quite neatly and integrates with many, many different constraint solving paradigms. And as a third ingredient, we reach neurosymbolic program synthesis in our wonderful library called HerbJL. We have Narcissus. Narcissus is this entire LLM-guided program synthesis, LLM-guided neural program synthesis on the one side. Then we have the symbolic constraints on the other side. And this gets combined into a neurosymbolic program synthesis because by definition, they work quite neatly together. This is what we wanted to reach in the first place. And well, as a summary, LLMs guide our search towards plausible programs, and the symbolic constraints prune undesirable ones. Summary and conclusions. Some core messages. On the neural side, LLMs are excellent at proposing plausible programs. Program synthesis is excellent at enforcing correctness and actually checking correctness and reasoning about what useful programs can be. Well, we can attempt to combine both by analyzing the underlying graph structure. So first off, on the neural side, we can try to reproduce the proposed structures from the LLM. On the constraint side, we can also prune away programs by analyzing the graph structure. And fourth off, everything is program synthesis. This is probably going to be a proposition also at my defense somewhere, because many programs can be actually encoded into program synthesis. Anything that has an action inside and so on is eventually a program synthesis. TLDR, last comment on this. Talk to me if you're tired of writing your own code or writing differential equations or whatever process. Come talk to me or scan this QR code, which is going to link you to our wonderful program synthesis library, where we do program synthesis and actually have many cool applications in bioinformatics and router design and logics and programming language stuff. Thank you for your attention.